Okay, so it's 4:30. I think we can start. So welcome to this presentation. We have Dr. Gault with us. We are very happy that he accepted our invitation. And Jaya will introduce as well as conduct the session. So it's over to Jaya.
Yeah, hello, and thank you, Guru. I would like to begin by thanking Professor Baptiste Gault, who, like Guru said, accepted our invitation and agreed to come over and join us, especially to our students, to interact with them and present all his knowledge that is gained over the years in the development and applications of atom probe tomography. Professor Baptiste, or what he would like to be called as BAT, I suppose, holds a joint holds a joint appointment between Imperial College London and Max-Planck-Institut for Eisenforschung in Dusseldorf, where he's the group leader for Atom Probe Tomography. Since February 2018, he is also an ERC consolidator-funded group targeting hydrogen in metals using APT techniques. Dr. Gault obtained his PhD in physics in Rouen in 2007, where he developed a new generation of pulse laser atom probe microscopes. So you are basically talking to the guru of APT. He then worked as a research scientist at the Australian Centre for Microscopy and Microanalysis at the University of Sydney, and in between also held intra-European Marie Curie Fellowship at the Department of Materials, University of Oxford, where he worked on thermoelectric materials. So as he had this repertoire of different materials and he was gaining experience with characterization tools, he also had a brief stint as a senior publisher in the material science group at Elsevier, looking after the materials engineering portfolio that comprises Acta Materialia, Scripta Materialia, and so on. Since April 2013, he's also been an academic visitor at the Department of Materials, University of Oxford. And in 2016, when I was just actually getting out of MPIE, he joined as group leader in Dusseldorf. And he's been awarded last year one of Germany's highest or the most prestigious research funding prizes, the Leibniz Prize, for his work and for his continuing work on APT techniques. I would also like to highlight here that he's the editor for Materialia and an associate editor for Acta Materialia and Scripta Materialia. So without much ado, you have here to talk about everything that we need to learn about APT techniques. Thank you.
I'll do what I can. It's very humbling. Thanks for having me, and I'll try to be thorough, but also broad. So I won't go into a huge amount of depth, but anytime you have questions afterwards, just feel free to ask, even in between, if you feel that, you know, I'm saying something completely obscure or arcane, feel free to ask a question, right? I think that's the purpose of this talk, especially for students. I think it's important to be daring at times. Anyway, so I'll talk to you about Atom Probe, and yes, I'm based at the Max-Planck-Institut für Eisenforschung, so in the west of Germany, right here in Dusseldorf, and I hold this joint appointment in London. And normally I'm supposed to spend like a week or term in London, which hasn't really happened in the past 2 years, as you might guess. So that's the institute down there, and our motto is to look at complex materials in real environments down to the atomic scale. So the institute has 4 departments, but 3 that are really active. The 4th one is its head is on leave from the institute to be the president of the Max Planck Society. So when Jaya was around, I think she was probably somewhere in that building, and that's what the institute is like. So that's the brick wall right at the entrance, and that's where we do Atom Probe here. I'm pretending to do Atom Probe because I don't really do that, right? Just a group leader, so I just support people doing their work. And that's where we forge blades and new alloys somewhere across these halls. MPIE is really interesting in the sense of everything that we can do in-house already. So we have big TMs here and a lot of mechanical testing facilities in there, and we can synthesize materials and get it processed, and we can go down to looking at these atoms, which is the purpose of today's talk. So why do we do what we do is always a good question to ask in the first place. So if we think about a piece of metal, in particular a material, but mostly metals is what we tend to focus on. We look at how the atoms are arranged on a crystalline lattice, and then there's a whole hierarchy of stuff that actually doesn't necessarily fit in that lattice perfectly, right? So sometimes we have a foreign atom in the lattice that comes in, that substitutes to one of the atoms of the lattice originally, so one of the substitutional solutes. We have sometimes an atom missing, so a vacancy, which forms another type of defect. We can have smaller atoms like this that come in between the atoms of the lattice, so these interstitials, and then there's also defects in the way that the lattice is arranged. So sometimes you have an additional line of atoms, a plane, an additional half plane, like a dislocation somewhere. This can also happen when you're starting to deform the sample. You can have just the lattice twisting like this or forming these twins. And then the way these crystals of the crystal lattice all form, they can have different orientations with respect to each other, which is also going to affect the material's properties. And then some of these foreign atoms can go and segregate to the boundaries, or they can be voids. And then you keep going like this. And then when you have mixtures of different elements, they can form different phases, secondary precipitates inside of a grain, or just a bulk phase that might occupy a full grain. And all of this then interacts with the environments through all sorts of possible reactions that can take place, and all go up to the surface there, where all sorts of junk can happen. The thing is, all of this happens from the scale of a couple of atoms to millimeters, meters, kilometers, maybe not. Although when we start thinking about pipelines, it can be kilometers. So all of these features are going to require a range of different tools, so we can actually look at them and try to understand the way they all interact with each other. And when we start thinking a little bit about materials characterization, there's a number of techniques that spring to mind beyond optical microscopy. There's all of the scanning electron microscopes and transmission electron microscopes, sometimes also operating in scanning mode. And then what we often want to do is look at the microstructure, the structure of the atoms, but also what is the local composition? What is the local mixture of different atoms from different elements? And for this, we can use, for example, EDS, or X-ray energy dispersive spectroscopy, or EELS, so when we look at how the electron lose energy as they travel through the sample, and then we can get from this a number of information on the local composition. And then there's also techniques where we, like SIMS, so secondary ion mass spectrometry, where we have a primary beam of ions that is going to sputter the surface, and then we do mass spectrometry based on this. And there's a space here, somewhere down there, where we can want to look at small features, and with a range of sensitivity, chemical sensitivity, roughly in the part per million type range. And that's where the atom probe is sitting, basically. And that's why we do atom probe, is to look at stuff that's not really a millimeter in size or a micron, but in between a nanometer and a micron. And when we want to look at small concentrations of elements. And I'll get back to some of these aspects later on. But that's just to position where we work. So we don't look at big stuff, we look at tiny stuff. And we can go down to measuring small numbers of atoms. And that's what a needle for atom probe looks like, and I'll explain afterwards why we need this. And what we've been trying to really push at the Institute over the past, whatever, decades, or even before I started, was the ability to combine the structural information we can get from a transmission electron microscope. So here we have a precipitation strength and austenitic steel, and you can see there's a matrix and there are precipitates, and the atoms inside the precipitate and the matrix are not arranged exactly in the same way. The precipitates are ordered on the long-range ordering, where we have certain atoms occupying a certain site of the lattice and other atoms occupying another site. But looking at these types of specimens through the lens of the TEM, we get a through projection through the entire specimen. So we have just an idea of how the sample looks like when we look through this, not exactly where each atom is located. And then the capabilities to measure composition in the TM are also sometimes limited. So what we may want to do is combine this information on the structure with the information we can get, for example, from the atom probe, where we might not have exactly the same accuracy spatially. And again, I'll get back to this, it's still the introduction part, but we get locally what is the composition of the material, including, for example, for carbon and aluminum and manganese and iron. which can sometimes have very similar Z numbers, so very close atomic weights if you want. So if I do look at one of these columns, I can't really tell you whether the dark bit here is iron or manganese because they more or less have the same weight. But from the atom probe, I can tell you that within one of those precipitates, I know exactly how much of each of the species there can be. So these particles, these precipitates are actually carbides. So they will contain quite a lot of carbon, which is also a major challenge to measure by electron microscopy techniques. So how does an atom probe work? Let's go back to really the basic physics of how that works, because a lot of the interests or qualities of atom probe and also a lot of its drawbacks and problems actually arise from this principle. So if I take a surface and I consider just a single atom sitting on the surface and I apply a high electric field, so I can just apply a high voltage onto this surface and then it's going to translate to a high field right at the surface. And if the field is high enough, the surface atom can start to be repelled from the surface and potentially ionized. And now I have an ion in an electrostatic field. So as you might guess, the field is going to accelerate the ion and the ion will fly away. So it's as if it was projecting this atom, first making it into an ion and then projecting it away from the surface. So this combination of desorption, ionization is called field evaporation, and that leads to the projection of these ions away from the surface. And this field evaporation requires fields that are 1 to 6, typically 10 to the 10 volts per meter, so 10 volts per nanometer roughly, which is not exactly small. It's actually quite big. And how can we generate such fields? So we could either put 2 plates with 1,000,000 volts separated by like 100 nanometers, and you probably don't want to be close to this because there might be a lot of other problems associated to doing this. What we can simply do is, if you may remember some basic electrostatics from undergrad, is if you take a sphere and put it in vacuum and apply a voltage V, the field at the surface of the sphere would be V divided by the radius of the sphere. So what we are actually doing is not exactly taking a sphere and suspending it in vacuum, right? We just take a very, very sharp needle, as I've shown you from the TM image before. And then at the ends of the needle here towards the apex, near the apex, we have a surface that is highly curved, which is more or less like a sphere. And if we apply a voltage of a few kilovolts and the radius here is in the range of tens of nanometers, if we divide one by the other, we get to the right range of about 10 to the 10 volts per meter. Because this is not a sphere, we have a geometrical parameter here, which we sometimes call field factor or field reduction factor, which is somewhere between 3 and 10, depending on the specimen geometry and the microscope geometry. But basically, with just a few kilovolts and a sharp tip, I can get to the fields that I need to start removing atoms from the surface of that very specimen. So how do we make sharp needles? We can do this by electrochemical polishing, like the specimen that you've seen before. Increasingly, we do this using a focused ion beam. So it's like an SEM, but on top of the electron beam, we have a secondary beam that comes in that is typically either gallium ions or xenon ions. So we can use it to actually sputter the surface very locally and dig trenches. So we can start digging a first trench, a second trench, then come in with the micromanipulator, all of this inside the fib. And then with the gas injection system inside the fib, we can weld the micromanipulator to this little bar of the material that we are interested in, and then lift it out. So now we have a small piece of the material of interest that is outside of the bulk, and that we can use then to deposit onto a support. We're going to come in and slice a small piece of that material after we've welded it onto the support. And then we cut it free, we can remove the bar, and then we have just that small piece of the material here that really contains what we are interested in looking at. And then that small piece of material we turn into a needle by using a series of annular milling patterns to go from this chunk into this sharp needle. So the interest here is that we can use the array of different techniques, SEM-based techniques like EBSD or EKI or simply backscattered electron imaging, or to actually look for a feature that can be interesting, like a grain boundary or specific phase or a specific grain or a grain of a specific orientation. And then we can cut it with the fib, make a needle, hopefully the feature of interest will be somewhere here within the needle. We are getting quite good at doing this. It's not always a 100% success rate, but we're getting quite good at doing this. And then we stick that needle into a ultra high vacuum chamber, so in the range of 10 to the minus 10 to 10 to the minus 11 torr. We have this very sharp needle. We cool it down because we don't want the atoms to start moving around. During the experiment, we want them to stay still. And then we apply this high voltage. The surface atoms will progressively turn into ions, and they're being projected away. And they're being projected away along trajectories that are defined by the shape of the needle and pure electrostatics, right? So you apply a voltage, the field will distribute across the entire chamber. So depending on the position, for example, of this counter electrode with respect to the specimen, you will have a distribution of the field that is modified. These days, we typically have only about 40 microns distance here, and we can address one of these specimens, just one, even though we can prepare multiple on this support that I've shown you before. And then these ions will fly, and what we can do is collect them on a detector. So we can use different types of particle detectors. We use a detector that is actually sensitive to the impact position. So we can record where the ion is landing on the detector. So because we sort of know these trajectories, we'll be able to use that information later on. The second aspect is that we want to be able to time the moments when these ions are created. So there's two ways to do this. Either we want to increase temporarily the field, because the probability that the atom is going to become an ion and field evaporate is proportional to the strength of the field, the intensity of the field. So I can just, on top of the DC voltage, apply high voltage pulses directly on the counter electrode, so they would be negative. It's going to repel the electrons a little bit more, and that's going to increase the positive field at the apex of the needle temporarily for a couple of nanoseconds. Or I can just focus a laser tightly towards the end of the needle, and the needle is going to absorb some of the photons from the laser. Its temperature will increase for, depending on the specimen, sometimes just a few picoseconds, sometimes a bit longer. And this increase in temperature would actually assist with the field evaporation, which is a thermally assisted process. So the agitation of the surface atoms, the intensity of the field, at some point the atom can just be agitated enough that it just hops away, transition into an ion, and then flies away. So knowing when the ion is created, and we can also look at when it lands on the detector, so we can actually measure the time of flight of each ion. And you can imagine that if something is a big fella like tungsten, it will just travel quite slowly. If it's tungsten bearing more than one charge, like 2, 3, 4, it has lost 3 or 4 electrons, it's going to be accelerated a bit more. But then if you're looking at something like carbon that is really light, it will just travel much faster. So there is a direct proportionality between the time of flight of an ion and its mass to charge ratio. So we can directly use this information to identify which element was each of the ions that we've detected. And then I'll tell you a little bit about the magic that we use to go from this information in 2 dimensions plus the time of flight into a typical atom probe data set that would be a point cloud like this, where every point is one ion that was detected. And the color we associate to a specific element. So for example, this is silicon for photovoltaic applications. There's a ground boundary here that is faceted, and we can see carbon segregated at the 2 facets, and primarily here at the junction between the 2 facets. So this is the type of information we can get from atom probe that would be really hard to get from any other technique. So as I said, atom probe is first mass spectrometry technique. So the first thing we get from an atom probe experiment is something that would look more or less like that, a mass spectrum. So we have a histogram of how many ions of a specific mass to charge ratio that we've detected. So we can go down, if I zoom in, we have isotopic resolution. So I can see the different isotopes of chromium. You can see the vanadium here in between the isotopes of chromium. Then there's the isobar with iron, and we see all of the isotopes of iron. This one missing. No, they're all there. And then there's manganese here in between the iron 54 and iron 56. And these are all in the 2+ charge state. That depends on the elements and the strength of the field. But that's the first information we get, is the piece of material that I've basically broken down atom by atom. I can tell you what it contained initially. And then, as I said, we have these detector coordinates and the time of flight. And then we sort of assume that the atoms, the sequence in which we detect them, must reflect the depth at which the atoms were initially, right? Because if you have an atom on top of another one, this one must come off first before the second one can come off. So we make an assumption that it's true. But if we do this, we can use that sequence to progressively build the third dimension. So that's what we do. We assume that the ion is basically emitted by a virtual emitting surface. And then we take the position of the ion impact on the detector, and we reverse project it onto this surface using a typical projection law. So we use something that is a bit like a stereographic projection, which you might have heard of. It's not exactly right, but it's not so bad. So we reverse project this position onto the emitting surface, and then we just shift this emitting surface down by just a tiny amount corresponding to the size of the atom that we've detected. So a bigger atom will tend to be causing the surface to go down a bit further. Again, it's an assumption. It's a model, like most of what we do, but it works okay so far. And then we take the second atom and we position it back on this new virtual emitting surface, and then the third atom, and we do this sequentially. And every time we process one atom, we move the surface down, and process one atom, move the surface down. And so that's the way we build this 3-dimension. So it's not perfect, as I said, it's a model. We have to make assumptions, but it's not so bad. There's also the physics that's playing some tricks and limiting what we can do. So first, if we look at the distribution of the electric field at the apex, what we have is actually something that is rough. I'll get back to this in the next few slides, but basically the surface is not smooth, right? Down at the atomic level, we are trying to make something spherical out of an assembly of atoms that's typically on a square lattice or a cubic lattice. So we always end up with a series of terraces. And these terraces actually cause the field to be not homogeneously distributed, and there will be slightly higher field at the edge of the terraces because these atoms have basically less neighbors to share their electrons with them, so they are a bit more exposed to the field. And so instead of having this atom right there from the edge being projected along this straight line, it might roll up a little bit to the side, or it might roll up on its neighbor before leaving. There are multiple paths for the ion to leave, which means that when we detect it, it might not actually have, when we reverse project it afterwards, we might not position it back to where it really was, but slightly sideways. And then the detector that we use doesn't detect all of the ions. Typically, they are making use of macrochannel plates, which are like a series of small, tiny photomultiplier, basically. So we have an ion coming into one of the tubes, and it will trigger a cascade of electrons. And we typically have 2 of those macrochannel plates positioned one after the other. And it means that for one ion coming in, we typically detect about 1 million electrons, which is much easier to detect than a single ion. The thing is, these glass tubes that you see, we can't have 100% of the surface that is active. We basically always have a certain amount of the surface that corresponds to the junction between all of these tubes in some ways. So we are going to lose, depending on the geometry of the detector and the generation of microchannel plates that we use, we are going to lose between maybe 10% and 50% of the ions. But this is random. It just depends on where they land on the detector. It doesn't depend on their mass, or it doesn't depend on their acceleration energy. So normally, if all goes well, we don't have species-specific losses like you could get from TEM, for example, because the low atomic number species are much harder to detect. But if we have a specimen where atoms are perfectly arranged on the lattice like this, after the field evaporation process, collection of the data and reconstruction, often we get a sort of a mishmash of points like this. And it's not fully bad, right? I'll get back to some of this afterwards. We still have a very good resolution. But sometimes it's kind of difficult to answer the typical question of what's the resolution, because these trajectory aberrations are not controllable in some ways. So it's not like we can make an aberration corrected atom probe anytime soon. But still, again, that's a typical atom probe data set. This is for nanocrystalline aluminum. You can see it's all in 3 dimensions, and here I have different species. It's a 7000 series, so I have some zinc and magnesium and copper. I have multiple grains. It's nanocrystalline. It was all deformed, so I can see some precipitates inside of one of these grains. I can see some of the solids segregated to a boundary and to another boundary. A precipitate right there sitting at one of the boundaries. So these are 2 mirror images. And I can select, I may want to see where's the aluminium, where's the copper, where's the magnesium, where's the zinc. And this is really the information that we get from the atom probe. It is a 3-dimensional map of composition. And so I can look at some of these precipitates in details. I can try to measure the composition and the way the composition evolves near the precipitate and inside the precipitate. The thing is, because sometimes, as I said, we need to assume that the atoms are coming in the right order. And when they do, which is most of the time actually, we have the resolution in the Z, in the depth, to actually image atomic planes. So in that case here, in this grain, I can see some of the 113 planes, and here I can see some of the 002 planes. And because they're more or less superimposed within the data set, I can tell you that we had one set of planes like this and the second set of planes like that. So we've crossed the grain boundary. So we have a lot of information there that we can use. I'll get back to this in the next few slides because I think it's quite an important feature. But again, what sort of information we can get from this distribution of points? This is a nickel-based superalloy that was built by electron beam melting, so one of these 3D printing fancy techniques. For example, I can do a composition profile through there, and I count how many atoms of each species I have within a certain bin size or cylinder that I can define, all in 3 dimensions. So I can see, for example, that there's a very strong boron segregation right at this grain boundary. And then I have the composition of gamma, which is this phase there that contains mostly, that contains chromium. So that's why it's a bit pinkish. And then I get into a very large primary gamma prime that is on the other side of the grain boundary. So it's nickel rich and aluminum rich. So that's sort of the information we get. Also, I can isolate one of these particles, for example, and then look at the way the concentration evolves as I go in and out of the precipitates. So these are typical measurements that we would make. And then because I have this assembly of points, I can also look at an aluminium atom. And where is the next aluminium atom? Is this distance compatible with a random distribution, or is it not? And if it's not, then it might indicate that there are tendencies for the aluminium to agglomerate, so maybe some clustering tendencies. So I think in that case, it's an ordered phase, so it's probably a bit more complicated than this, but just to give you some hints of what we can get out of it. So as I said, we sometimes have this crystallographic information. We can see planes in the atom probe. So about 10 years ago, when I was a bit younger, we looked at this quite a lot. And my boss in Sydney decided to coin this the atom probe crystallography approach, which I'm still not completely sold as a terminology, but that's a different problem. So as I said, we have some trajectory aberrations. And so it means that when we look at the distribution of the atoms on the detector, we see a pattern forming that corresponds to where we have some of these terraces forming. I'll go into some more details afterwards. But this might actually remind you of a pattern that you might have seen in the past, like these Kikuchi bands that we often see in the TM or in electron backscatter detector diffraction. But also, let me show you this. So here you see a certain pattern with a 3-fold symmetry, and then there's another 3-fold symmetry here. This is a 1-1-1 direction popping out of the specimen. And I'm just showing you one small histogram of these ion map that are coming during an experiment. And if I go down inside the specimen and look at the way the detector map evolves, I can see that it's changing. And here you can see actually this is the same set of planes, but across a grain boundary that is right there. And you can see some contrast here that pertains to the point density can be higher inside of precipitates, for example. So there's quite a lot of information in these maps that we can use. But here you can see clearly that we've crossed a grain boundary, and we'll be able to analyze this grain boundary in quite a lot of details. So again, why do we have this sort of patterning on the detector? If I take this assembly of dots of spheres, and I try to make a needle out of it, you'll really end up with something. If I look from the top, it will look like this. So it makes a series of terraces, right? And if you have time, you can try to decide to, make a Death Star out of Legos, and you will find exactly the same patterns forming. It will be a simple cubic lattice, but it's already a good model. So maybe it's a good excuse to use research funding to buy Legos. It's up to you. We haven't done that yet, but I wish we could. But anyway, so that's basically what you see here are these different crystallographic directions popping out. And this is exactly what we find inside of the atom probe data as well. So again, when we look at these terraces and the edges of the terraces, we'll have these trajectory aberrations forming. For us, it's actually quite good because if I look at this pattern from a pure aluminum specimen, I can actually determine, based on the symmetries, I can determine what set of plane that is and what set of plane that is and what set of planes that is. And I'll be able to image these atomic planes right where they are across the field of view. So now I can see these different sets of planes. I can interrogate the data along these different directions to look at whether I can actually image planes, which one they are, and I can measure the distance between the planes. So this can be very useful sometimes when we want to look at, for example, this is a Martin stick steel, and we did EBSD beforehand. We lifted out from a specific grain, knowing that the direction, the 111 direction, would be quite close to the main axis of the needle. So when we then do the experiments, we have the 111 direction very close to the center of the detector. So the 111 set of planes will be very close to the center of the detector. And then we can start to look at whether we find these atomic planes inside of the reconstruction, and we do. And then we can use this information to identify on which planes some of these very early stages of the carbides that are forming, on which planes are they sitting. And then we can see that they are located at 90 degrees from each other. And we can determine that with respect to the main orientation of the needle, they're actually sitting on the 100 planes or 200 planes. So this can be also very interesting and important information when we want to identify some of the phases that we detect, and especially when some of these phases are very early stages and metastable phases that have not necessarily been documented before. But if I get back to some of this aluminum data, so that's the maps I've shown you before with this short movie, I can see that this is the grain boundary that I've analyzed. So I've crossed into it, and then it's going straight down the data set afterwards. And I can go down to, again, looking at how the atoms are arranged within the grain boundary, how are these precipitates arranged with respect to each other, what is their composition. And in this case, we actually could find some compositional fluctuations with a period that corresponded to 11 111 planes, and it actually happened to be a sigma 11 grain boundary that we took at more or less at random, so we're quite lucky. But we can get to that sort of level of information with the atom probe when we start digging into the data. It's not readily there always, and it's sometimes difficult to get to the point where we can extract this information, but very often it's there, and that's why I have a job, because I know how to do that in part. But that really begs the question of what are the limits of the spatial resolution that we can achieve, right? So again, if I look at some of these data sets, I can see a lot of atomic planes across this tomographic reconstruction that I've built. I can do Fourier transform, for example, to see that effectively there are planes, and there are almost like a diffraction pattern that we can form based on the spacing of these planes. We'll have a series of spots that form in the reciprocal space. I can also use other tools to look at the average distance between atoms within going straight down this set of planes here, or that one, and I can measure the distance between planes. And typically, if I do my reconstruction properly, it does match with what we would expect from the crystal that we know we have, in that case, pure aluminum. It's pretty simple. So we know we can do things not so badly. But as I told you before, the biggest issue is not in Z. The biggest issue is in XY. Laterally, some of these atoms are going to be repelled away from the center of the poles. So I can also look within one of these planes, what is the average distance between the atoms? And in that case, I can see a pattern forming. So I'll get back to my laser pointer. I can see a pattern forming that actually corresponds to what I would expect on a O2 plane or 111 plane. As you can see, the 6 atoms sitting there, so the really dense, closely packed planes. The thing is, if I take a slice through one of these maps, I can see that there's very, 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 very few of the atoms that are reconstructed properly. Most of them are in the background somewhere. So laterally, we are losing the interatomic distances, but in Z, we are reconstructing them properly. So these are informations that are really quite important to bear in mind when we analyze data, and when you guys might encounter atom probe data sometimes in papers. It doesn't mean that it's wrong. It means that, like every single measurement technique, we have to be aware that it has limitations. And we actually made a big mistake interpreting data about 10 years ago, and I like talking about that story because it sometimes sounds so self-correct, right? So we looked at this, sorry, my wife's phone is actually ringing, so I need to shut it down somehow. There you go. So we looked at a similar set of alloys, aluminum, copper, lithium, magnesium, silver. And in that first paper in 2011, we actually thought that there was no segregation of any of magnesium or silver at the interface between the precipitate and the matrix. And this is because we didn't look where the resolution was the highest. And then we looked at similar alloys a bit further, a few years later, and we looked at these alloys with the set of planes, the one-on-one set of planes positioned in the center of the detector in a way that we could actually maximize the spatial resolution. And if you do this, you can see that effectively silver and magnesium, so silver is black and magnesium is green, are segregated right there at the interface between the matrix and the precipitate. But as you start to go away from where the planes are visible, where things are a bit more messy, it's almost impossible to tell that there is this segregation. So we made a mistake. We've learned a bit since then. That's why we progress all the time. But when it gets messy, it can be really difficult to sometimes make sure that we are in a position to conclude what we conclude. But again, I mean, in 10 years, I've lost hair quite a lot, but I've learned a lot more. And if we look at, for example, this is an interface. It was a transformation interface between austenite and ferrite in a piece of steel, which is a model alloy. I can look in the top grain and the bottom grain. I can see here that there's one of these regions that has a low density corresponding to a set of planes. It's actually continuing through this interface that was inside of the material. So I can look and see, you can see the planes here, they're well organized. And I can see how the resolution is going to affect the compositional measurement as I go through the entire interface. And so I did this, I just fitted a Gaussian to get some sort of value that made sense and get a forward half maximum of the profile. And what I get is that right on the pole where these atomic planes are well reconstructed, I can see that I get something for the width of the profile will be 0.5 nanometer, so just 2-3 atomic planes maximum. And same thing for the manganese, it can go down to about 0.5. So only the segregation will only take place over 2 to 3 atomic planes of the iron matrix. There are fluctuations along the way, and you can see that, and it's partly because actually there's a slight mismatch in the orientation relationship between the two grains, which mean that every maybe 20 nanometers or something, there's a need for a dislocation to accommodate the change in orientation. And these dislocations actually suck up a lot of the manganese and carbon. So it made my analysis a bit harder than it should have. But we can actually go down to imaging how much segregation there is right at this interface. So it's quite an interesting case for me because the guys in France actually published that paper, and then I looked at their data again and I showed them that they were wrong, which was quite fun. I mean, they're friends, so they didn't mind. But I think it's really an interesting case of data that was not interpreted really properly. And if we start scratching the surface, there's a lot more that we can say about it. So it's one of these things where we actually could get down to showing that if we prepare the samples in the right orientation with the right to maximize the resolution of the analysis, then we'll probably get results that are more meaningful and more interesting from a material standpoint. So as I said, for the matrix, we have sometimes some of the small aberrations taking place. And it can become a bit more tricky at times because if I consider a particle inside of the matrix, the bonding inside the particle will necessarily be different. It means that I will either require a slightly higher electric field to remove the atoms or a slightly lower electric field to remove the atoms. Which means that also these atoms from the particle, they will not really leave in the right order, right? Because if they need a higher field, for example, the fields that I need to remove the matrix atoms and the ones from the precipitate won't be the same. And we need to have basically locally a higher curvature forming to increase the field. And once the field is high enough here, I might be in a position where I can start to remove the atoms from the precipitate. But in between, this higher field is going to push some of the atoms from the matrix very close to the particle. They're going to be pushed away a bit further than they should. And then the atoms from the particle itself also are going to be pushed away slightly more. So there's another limit of resolution, which is not just from a pure metal matrix, but also as soon as we have macrostructural features that are really what we're interested in. So this has been well documented and well studied through finite element method simulations, mostly from about 20 years ago. There's quite a lot of information on this. If you're interested, we can talk about this later. But what we showed last year in comparison between small angle scattering data, so either X-ray, small angle X-ray scattering or neutron scattering, and atom probe, is that the atom probe and small angle scattering sizes seem to match for particles that are above a nanometer, roughly, give or take. But below a nanometer, these trajectory aberrations are going to make things much more complicated in terms of measuring the size. We're still detecting the atoms. We can still derive a composition locally, but there will be a bit of intermixing between the matrix and the particles. So sometimes we have to be quite careful with the way we interpret the data that we get. And in the last few minutes, I just want to walk through a couple of examples of applications. So this is work that was done mostly by Surendra McKinney, who is now at the Indian Institute of Science, so not too far from you guys. He's running in part the Atom Probe group there, so I think it might be interesting for you to talk to him if you need. But what we wanted to look at were some of these cracked cobalt nickel alloys. And as they get prepped to fracture, we see that these gamma prime precipitate that were initially cuboidal, they've extended in one direction, so this so-called rafting. And there are many dark features as we look through these samples in the SEM. And these correspond to stacking faults that are formed within gamma prime. So then we did electron channeling contrast imaging. I can get back to some of this if you're interested later on. We can go down a specific zone axis with the specimen oriented in a way that we can image the stacking faults. We have these 4 variants of the stacking fault. And then we develop pathways to take one of those stacking faults, lift it out in the fib, mount it, do TEM on there, so we can actually image it in the TEM in high resolution, see that it's a super intrinsic stacking fault, and look at the way the atoms are arranged along the fault. So in that case, it's getting towards a DO19 structure and not an L12 anymore, because you go from an FCC organization to an HCP organization of the atoms. And then we stuck this sample into the atom probe, and it took us quite a long time to actually find out that the stacking fault was inside the data. But then when we looked at it, we just zoomed onto this region, and what we found was a tubular region that was really high in chromium, and that actually correspond to the leading partial dislocation that has crossed into gamma prime. And on the wake of that dislocation, we can see here, for example, a region that is depleted in aluminium. And because of the high resolution stem that we had done before, we knew that it was most likely segregated by something heavy. In this case, it would be some tungsten. The interest of the atom probe comes now, and its strength is that we can interrogate this point cloud in whichever way we want locally. So we actually looked through the linear defects, this partial dislocation. We can see effectively a very strong segregation of chromium, depletion of nickel, segregation of cobalt, depletion in aluminium, and in tungsten a little bit. We can then also look through the fault itself. We see a slight segregation of cobalt and tungsten, depletion of aluminium and nickel. But then we can also look ahead, like along this planar defect, right ahead of this partial. What we see is that there is an increase in the aluminium as if it was being pushed by the moving dislocation. And we can see that there is a depletion of tungsten right ahead and a segregation of tungsten on the fault. And this we interpreted as the tungsten from in front of the fault being sucked in by the partial dislocation and then positioned onto the stacking fault itself, where actually it makes sense because this GO19 structure is very close to CO3W. So we see a segregation of cobalt and tungsten that would be expected. Why we propose this mechanism is because when we look through the fault, we don't see any depletion of tungsten on either side, right? So the tungsten must be coming from somewhere else. And what we interpreted this in the way is that the dislocation as it moves actually facilitates transfer of tungsten from ahead of the partial directly onto the fault. We did a lot more work on these things, looking at rhenium, for example, into some of these alloys, but I'll probably skip that and can talk about it later if you want. Anyway, so just to conclude, what Atom Probe does well is to provide a three-dimensional compositional mapping of solid materials, and mostly bulk, but also thin films. We can look at oxides, nanoparticles also, but it requires some tricks. But that gives you an idea of how are the species distributed within your sample. And it's cool, but there's some pretty complex physics behind it. So sometimes the interpretation is not as straightforward as we would like it to be. It doesn't mean that we shouldn't do it. It means that we have to be a bit more careful sometimes with the interpretation. But again, that's like any measurement that we make. Again, there's very variable insights from Atom Probe, especially when we start getting into looking at carbon, for example, or some of the very low, low amounts of lighter species, mostly because other techniques like XPS or SIMS or TEM will not get you this combination of high sensitivity and high spatial resolution, or they might get you only a one-dimensional profile with high resolution or a through projection, which sometimes is not sufficient when we start thinking about very complex macrostructures. And final point is that, I think we need more people doing Atom Probe in the world, and that's been challenging us doing just Atom Probe now for the past 10, 15 years. It's been really good to have more people coming in and actually asking all of the questions that the community has been hiding for a long time. So I think we're better now than we were 10, 20 years ago. I think it's really clear. There's still stuff that we don't do so well in terms of communicating some of the issues that we face, and that's what I try to do today. I still love the technique. I think it still provides a huge amount of information that's extremely valuable that you would not get otherwise. We just have to be careful that, like any measurement, it has limitations, and we need to understand these limitations to provide the best possible interpretation. And I just want to acknowledge all of the people who've been giving us money to do what we do, from the German Science Foundation and the local doctoral school that has been providing us with really awesome students. We've had a lot of support from the Alexander von Humboldt Stiftung, with quite a lot of fellows coming and doing some really cool work with us. And MPIE, of course, that has been really supporting all of this work. It's really an amazing place to work. So thank you for your attention, and I'd be happy to take any questions.
Thank you so much, Matt, for a very comprehensive talk about the technique itself and how to make these measurements, and some very cool examples of some of the things that you did and what you did wrong. I think there are great learnings from what we do earlier to what we learn from them. So that's another important lesson for all
students,
of us.
Yes.
Students, yeah. Yeah, I think we're all learning in the process.
Yes.
So I would like to invite people to raise their hands, and then they can unmute themselves and ask their questions. So I will give a chance to Nikhil first before Guru. So Nikhil Dio.
Sure, thank you, madam. So amazing lecture. I mean, as you are called BAP, I think BAP would be in our language a better address to you, and you can get the understanding later. It means father, basically. So thank you very much for the amazing lecture. Most of the times, the output report that we see, or the output that we see, is similar to what you have currently on the slide, with few % of the atoms that are mapped actually. And most of the times we see that the purpose is to really understand the shapes of very tiny precipitates. My question is, what is the smallest limit of seeing the area? I mean, we don't really need such a big area. For example, if we want to understand what's the location of certain atoms in unit cell, can we perform this analysis on a very small portion, or can we at least map, let's say, 10 unit cells and try to understand where is, for example, in steel, iron, chromium, manganese, carbon, and things are lying with some ordinary rudimentary steels. By the way, another comment is, I was really happy to see that you have used this technique on simple materials like iron, manganese, carbon. So really happy to see that. And my question is, can we really do it on very small number of unit cells? Thank you.
So, I mean, you could, but then you're going to always have an issue of statistical. So there's two things here that I should point. So we typically measure small numbers of ions, right? I mean, it's always in the million range or tens of millions at most. So yes, we could make very tiny analysis, but then statistically speaking, our measurements would probably start to suck, and we need to be careful with how we interpret small numbers, right? I mean, the relative error of the measurement will increase tremendously as we lower the number of ions that we measure. So we have to be quite careful sometimes, especially, so, you know, if you look at a 50-50 alloy, it probably doesn't matter as much. But when we want to look at something like 0.5% of carbon in a ferritic matrix, we need to be a bit careful because also the smaller a region or volume you look at, the least likely it's going to be representative of the material as a whole. So I think we need to really balance these things. And yes, we sometimes can look at site occupancy. So whether an atom is sitting, sorry, as substitutional or interstitial. We need to be very careful when we prepare specimens for this, because we need to be along a series of planes where we sort of know there might be some ordering taking place, for example, or at least along which we should be able to accurately measure the interplanar distance and the position of these atoms in the z-axis. So what is the smallest object that we can look at confidently? It really depends a bit. So maybe I should get back to that graph. So here we didn't say which alloy it was because ultimately it doesn't matter that much. But here you'll find some aluminum alloys, some steels, some ODS oxide particles in steel. It's very varied, but the limit in resolution seems to be somewhere around a nanometer or 0.5 nanometer. So it's already hundreds of atoms, right? So if you start to think about this, you probably need to have it's probably better to go for a statistical treatment of a large number of particles and derive a number that actually has some sort of statistical error attached to it than to look at a very tiny number of atoms and then try to derive something out of it that might be wrong. So that would be my take on your question right now. But in principle, there are things we can do and tricks that we can play to really look at small volumes of atoms of a material, knowing what it, like along which direction we're looking at. So we actually maximize the resolution to make sure that we are as close as possible to giving an answer that's not too stupid. Does that answer your question?
Yeah, sure. Thank you very much. Maybe if I get contacts, then I might bother you by email later on. But thank you very much for the answer.
Sure, it's no problem.
Yeah, Guru.
Thank you, Jaya. Thanks, Dr. Gault, for the very interesting talk. Can we go back to the slide where you showed from the work of Dr. Contes on the superalloy with aluminum, chromium?
Yep.
So was the atom fraction of composition not corresponding to Ni3Al?
Yes. Like across here, so that gamma here. Yeah, I mean, I'm not showing all of the elements, right? So there's like another 10 elements that are that are in there. So because this was just for a paper that wanted to, I just didn't want to put all of the elements, but there's also, I can't remember, there's tantalum in there, there's cobalt, there's, so yes, you're right. It's not exactly N3AL. But if you add all of the gamma prime stabilizers in there, you would find something close to what you would expect.
And will this information help us know exactly what is the misfit, for example, in these systems? I mean, can this data be used to?
So what we're going to get is the composition. The misfit itself, not directly, because I think first it would be a very expensive way to measure the misfit. But in principle, what you're going to get out of it is the composition. And then this you can relate to the misfit. And there's been quite a lot of work done. And I mean, again, if you look in the literature around superalloys, there's quite a lot of work that has been done just in the partitioning behavior of some of these solutes one way or the other, whether they go to gamma or gamma prime under different conditions. And this then can explain some of the misfit that we see. But I think doing atom probe by itself, increasingly, I think it's kind of useless. We need to fit this within, you know, a bigger framework of different techniques that are going to provide complementary information.
And in NIAL MO, has there been any studies? Because that is a classic case where you can shift the misfit from positive to negative.
There's been a lot of work on this like 20, 30 years ago, so not really with the latest versions of the technique, but there's very often moly in these very complex alloys, right? So we sort of know how it behaves in some ways, but within these alloys with 10, 12 elements. On the model system side, just as nickel, moly, aluminium, I cannot think of a body of work that would have studied this. There's been a lot of stuff done from the Northwestern group on nickel, chromium, aluminium. There's been quite a lot done on nickel, vanadium, aluminium from the group where I did my PhD. But I think on moly, not so much.
Okay, thank you. Thanks.
No problem.
Yeah, since you stay on the slide, so I have a follow-up to this. This gives the composition across a line. I mean, it is akin to a line scan, right?
Yep.
But is it taking three-dimensional information and putting it?
Yes.
What does it do?
So here I have a big cylinder that I've positioned normally to the interface. I think it's about 40 nanometers across, and I'm putting it through the interface normally to the interface, and then every 0.1 nanometer, I put a new bin, and then I count how many atoms of all of the species I have in 3 dimensions. And then I add 1 point to the profile, and then I move to the next bin, and then I do the same measurement. So that's what we're seeing here. And that's why you can see here there are error bars, and they're very tiny because I count quite a lot of atoms. So statistically speaking, I'm making a measurement that's not too wrong.
And you had another figure after that to get the composition of a precipitate particle.
Yep.
So that is through another way of scanning the composition, or is it?
Yes, exactly. So here you can see I have superimposed on the point cloud. There is a series of voxels that are 1 by 1 by 1 nanometer. And in each of these voxels, I'm calculating the composition. And then I'm joining voxels that have the same composition. So here that's the blue surface basically encompasses or delineates regions that contain more than 5% aluminium. So here I can see a lot of smaller gamma prime particles within gamma. And then based on the position of the polygons that surround this particle, I can look at the way the composition varies as I move out and expand this surface. And then when I move in and I compress this surface. And in principle, this gives me the composition that actually evolves away from a particle that's not that cannot really be fitted easily with a cylinder or cuboidal region of interest. So that's often also what we see in papers. The problem associated to this is that we're starting from, a grid, a series of voxels. So we are losing also a little bit in resolution.
So the resolution is poorer in the voxel method compared to the cylinder. Yes,
I can send you papers on this.
Sure.
which everybody ignores, right? So that's the problem of being an expert at the macroscopy technique. You get very angry at people ignoring you. The stuff where you show that it's not perfectly as they think it is. But yes, so that's also why very often when people use these approaches for measuring composition profiles, there's always a rather smooth transition between the precipitate and the matrix. And this is in part because of the way the isoconcentration surfaces are calculated.
Right. Okay.
So I would use these profiles to get, what is at the core and what is away from it. Right at the interface, it can be much more tricky. For this, I would trust one of these small cylinders much more.
Perfect. Yeah. That was our question also, because we were looking at precipitates and interfaces where these precipitates were forming. So yeah, we'll go back and do that. Professor Raja?
If you have other questions or specific points that you would think I can help with at some point, just let me know. We can get online and have a chat.
Yeah, that would be really wonderful. But I will get back to you with the student who's actually doing the analysis.
It's no problem.
Yeah. Professor Raja?
Yeah, thanks. Yeah, and thanks, Professor Gault, for the very illuminating lecture. I think first time I'm attending a talk in APT. My question is related to hydrogen. How easy to detect hydrogen? Now, from the perspective of preparing a very small sample, first of all, will the hydrogen remain in the sample? Make it so small? Reminds how easy to detect the hydrogen content.
Yep. So this raises a very important point. So there's 2 or 3 things that we've also learned over the past few years. So first, if we do an atom probe analysis, almost all of the data sets that you will acquire always contains peak at 1, 2, and 3, primarily at 1, but also at 2 Dalton and 3 Dalton. So we detect hydrogen 1, just 1 hydrogen at 2 hydrogen, so H2 1+. And depending on the electric field conditions, we can actually form H3 1+. This is a metastable species, but it's well known in the high field community. It happens quite often. So the problem is that there's always some hydrogen in the chamber. There's some hydrogen adsorbed on the surface of the needle. So when we transport through air, even when we make needles inside of the fib or electrochemically, we are going to introduce some hydrogen inside of the chamber. Detecting inside of the specimen. So detecting hydrogen is not hard. The problem is the interpretation of the data. So will the hydrogen actually be coming from inside the needle, inside the sample, or will it actually come from the chamber and be just a spurious species causing problems? So we are not completely done with this. So what we are doing here increasingly, so there's 2 aspects. So first we try to introduce deuterium instead of hydrogen, and then in principle, if we are in the right analysis conditions, we should have mostly hydrogen coming at 1 and not at 2. So everything that is going to be in the peak at 2 Dalton should be deuterium, which we have introduced, especially introduced inside of the microstructure. And there we can actually look at where it's sitting inside of the microstructure. So there's been quite a lot of work done on carbides in steel that are used to trap hydrogen, and or some like highly deformed cementite particles in perlite, for example, that tend to trap a lot of hydrogen as well, whether it's trapped at the interface or inside of the particles. So this has been done quite a lot. The second point is that the hydrogen that we can see this way is typically hydrogen that is trapped. It's not hydrogen that is mobile through the matrix. And that goes to the second point. Is it going to stay in the specimen when the specimen is so small? So what we have been developing over the past few years are ways to prepare specimens at low temperature. So we go to liquid nitrogen temperature. We can actually do the fibbing at low temperature. So we make these needles at whatever 80 Kelvin or 90 Kelvin. And then we have a suitcase that we can use to transport specimens under vacuum and at liquid nitrogen temperature from the fib into the atom probe. And then we can do the analysis. So at the moment, there's maybe 5 or 6 places that are equipped with similar suitcases and devices. None of them in India as we speak, but it might happen, I don't know. So I think it really depends on what you're targeting when you want to look at hydrogen. So is it a hydride? A hydride can be analyzed like a carbide. It's going to have a small number of specific issues, but typically we can analyze it. So we've looked at quite a lot of hydrides in titanium or in zirconium alloys because they're readily formed, they're fairly easy to form. So we can look at the way, for example, so in Zirc, it was really quite interesting because, so it was a Zirc-4 alloy, so that contains tin. And we could see as hydrides were growing off from the grain boundaries that the tin didn't want to partition to the hydride, so it was actually being repelled away. And so there's actually quite a lot of interesting work to be done that not many people have touched so far. But when you want to look at mobile hydrogen within a ferritic matrix, for example, this is more difficult. And it's more difficult to actually get results that I trust personally. So we are still getting there. I think in a few years' time, we'll have better ideas of how trustworthy the data can be. That did not prevent people from publishing, right? But how much the data can be trusted sometimes gets me to scratch my head. But in principle, it can be done. So it's interesting. So I have a discussion with Surendra from Bangalore next week to discuss some of these aspects because I think there's quite a lot of interest there.
Yeah, thanks for the answer because, yeah, I mean, we have both trapped hydrogen or chemically reacted hydrogen like hydrides.
Yes.
But in some cases, the mobile hydrogen has more influence on the mechanical properties.
Yes, and this one is the one that will be hard to pick.
Very nice, and thanks very much for the answer.
No worries.
Yeah, next up, Siddhartha.
Thank you, ma'am. Hello, sir. Thank you for the wonderful lecture. It was really intriguing. I have a small question. Am I audible?
Yeah, go ahead.
Yeah, yes, sir. So while preparing the sample for a sharp needle kind of sample, I've come across a method called electrochemical polishing that's also used. They form a neck, and that's how they create the sample. So what's the differences between, I mean, what advantages does one method offers over the other?
So there's a couple of advantages that there are. So let's say it depends what you want to prepare. So from electrochemical polishing, you will be restricted to metals, so conducting samples. If you want to look at oxides or semiconductors, you basically can't really do this by electrochemical polishing. You'll have to rely on the FIB. The interest of doing electrochemical polishing is that it's cheap. It can be quick, and you can, once you have a needle that is good enough, you can run it. If it breaks down, you go back and you can resharpen it within minutes, and then you're just 10 microns down the shank, and you can keep doing it and doing it and doing it. So you don't necessarily need 10 sessions on the FIB to get quite a lot of data. The problem of this is that it's much harder to prepare a specimen from a very specific location within the microstructure. So if you're interested in a distribution of precipitates that are more or less homogeneous across the entire microstructure, then electrochemical polishing works. If you have the setup, which costs whatever the cost of an optical microscope and a loop of stainless steel, and it's really fairly simple to put together. A FIB and a good FIB is harder to get by. It costs money, and then you also have, it takes a bit longer to prepare specimens. I think overall, the time from a bulk sample to a needle is probably not that different through the two routes. But the advantage for me of the FIB is that you can prepare specimens specifically from a grain boundary, or from a grain that has a specific orientation, or from materials that are non-conductive. I think that's been really the key difference. I've worked on some aluminium plates as a postdoc about 10 years ago, and we wanted to analyze the sample along the 110 direction, and mostly it was along the 111 direction. So I had to cut some of these small matchsticks, at a weird angle and with the diamond. So it's just less practical. With the FIB, it would have taken me maybe half a day to get to the results that I want. But 10 years ago, access to a FIB was not simple. It's definitely not as simple as it might be today. So I think it really depends on the infrastructure that you have at hand. If you have a FIB at hand and an atom probe and not so many people, you probably don't need to develop electropolishing approaches. If you have one FIB for 50 people and it's also shared with people doing TEM and making whatever nanopillar for compression, and then developing an electropolishing rig probably makes sense.
Got it, sir. Thank you.
It's no problem.
No problem.
Kevin?
Yeah, hello, sir. Sir, thank you for that wonderful talk. I had a question regarding the analysis part, actually. So when we match the peaks that are there in that spectrum, what happens when you've got two elements having a similar position in the isotopes? If, like, let's say a titanium and a molybdenum.
Mm-hmm.
So in that case, which one do you assign it to?
So this is it's a good question. So the thing is, these elements have, we assume that they have the natural abundances. So it means that within that peak, where there's an isobaric overlap between chromium and iron, I cannot do this for every single ion. I cannot determine what it is. But if I take a small volume, I can do a statistical analysis and say, okay, I know that within this one peak where there is an overlap, whatever, 5% of the peak should be chromium, 95% of the peak is iron. Then I can derive the number of chromium and iron atoms separately.
So what you're saying is we should share the peaks based on the bulk composition. Is that what you're saying?
No, so I would do one analysis with the peak ranged separately from all the rest, and then do the analysis in some of those smaller regions. So in a profile, for example, I would call this peak, for example, here, I would call it neither chromium nor iron. I would count how many atoms there are in there, and then based on the number of atoms of chromium, I know how many atoms of that range I should have within this range that correspond to chromium.
Okay.
Okay, and
Yeah,
then the
because-
rest has to be iron. Okay.
Yeah. So because what happens is based on how we match these peaks is actually how the reconstruction comes up, right? So
in parts, yes, but I mean, the
Yeah.
difference would be only on the atomic volume, and it's quite small, the difference between iron and chromium. So overall, when you're doing this, as long as you're like during the reconstruction protocol, as long as you range stuff more or less as, you know, something close by, it's fine. I think it's more problematic when you want to derive the composition of a phase.
So the thing was that I was looking into certain precipitate shape and size. So I did this mistake of sharing all the titanium and molybdenum peaks. And what happened was certain weird results were coming, which I knew was not supposed to come. So yeah, I'll try the method that you just said. Yeah. Okay.
So you should call moly and tie only peaks that actually are moly and tie. The ones that have an overlap, you should call them separately. And then, but these are nasty examples. But yes, in principle, you can do this directly. You know, so you can calculate a profile and then recalculate the amount of each species in the profiles. There are, I think, a few tools that have been developed and that are available broadly and freely from, I think, from Aachen and from, I think there was one from MPIE, but I don't know if it's still accessible on GitHub. But it had been developed by one of the PhD students during her PhD 3-4 years ago. If you don't find anything, just ping me and I'll try to dig it out.
Yeah. Okay. Yeah. Thank you, sir. Fine.
No problem.
Yeah. Any other questions from participants? Maybe I will ask a couple of more questions if nobody else has any. So what about when we reconstruct glass samples with the reconstruction algorithms and things like nano glasses and structures like this?
Yeah, that's not necessarily an issue. We have the problem that we face is that the sequence in which ions come off is not as well determined as it would be in a crystal. So there is a loss in resolution that we can't really measure, because the way we measure resolution is by looking at atomic planes, which glass don't have. So, but we've looked at nano glasses and we've looked at So metal glasses have been analyzed quite a lot, and whether on the nano scale, like nano glasses or bigger bulk metal glasses, we can do that without too much trouble. We've also looked at actual pieces of glass, like glass, and that also runs. Some of the glass that is used on this mobile phones and stuff like that, we've looked at as well. In principle, it will work. I mean, the absorption might not be as good, and then and the heat conductivity will be quite bad. So if I get back to, why is this not working here? So here I can see all the peaks really nicely separated, because after the laser pulse has heated the sample can cool down quickly. So this basically the drop here in the peak corresponds to how fast I can quench the surface. But for some of these glasses that actually don't conduct heat so well, instead of having nicely defined peaks like this, you might have a long tail that will overlap with the next one and overlap with the next one. So it really goes down to what you might be interested in looking at in some of those samples. Again, in metallic glasses, it worked really quite well. There's quite a lot of literature on this. If you're interested in stuff, just ping me. I'll send you stuff, right? And it's not difficult to find.
So would that be also a problem for ceramics?
It can be a problem for ceramics, yes. But like, so there's still work that's being done on ceramics, and some of it works really well. Mostly on the instruments with the reflection, so instruments that are much longer in time of flight. So you basically make this these tails relatively smaller with respect to the peak. So it works fine. I mean, we've looked at aluminum oxide and a range of other oxides, and then there's a whole bunch of people looking at minerals and zircon and to do more like geochronology type things, and it works. I mean, again, the data is not as pretty as it would be on a metal, and sometimes the peaks will be broad and might overlap with other peaks, and that becomes a problem. But by tweaking the analytical conditions, maybe by lowering the laser power or increasing the voltage, or we can play around with some of these parameters to try and optimize the conditions. Okay. But again, I mean, probably the only thing that was useful out of my PhD was the fact that now people can actually look at oxides. So people have been looking at oxides and ceramics and blah, blah, blah. It's just that we don't have as much understanding of all the processes because it's a 15-year-old science in some ways.
Right, of course. Yes. Yes. Anyone else with questions?
Jaya, can I ask one more question?
Yeah, of course.
Yeah. So you said that segregation in the boundary is about 3 layers in iron manganese. Some of the
in that system, yes.
Right. So
yeah.
Are there also sort of rule of thumb for how much around the dislocation is the segregation?
So we found a whole lot of differences depending on the system that we look at. So for example, if I get back to this, so here are dislocations accommodating the misorientation between the two grains, right? And you can see that the segregation of manganese carbon would be about a nanometer or 2, maybe max, around this. This one that is slightly less segregated would have a profile that is slightly thinner. What we also see is that it's really not homogeneous all along. The dislocation tends to have broader regions, and this might be due to kinks that we just can't resolve. But there's really pretty work that was done. I can send you the link afterwards. Science Advances. Just give me 1 minute. And
so the kinks in dislocation is because it is sort of BCC kind of system, is it?
Yes.
They have a double kink kind of mechanism.
Exactly. But also, I mean, most of the dislocations that we've been able to image are always a bit They're never straight lines like this, right? That's a textbook, one of these textbook lies, I guess.
So do you also then see differences in segregation because the nature of the dislocation has changed? Because sometimes...
Yes. So you can look at that paper. So what Red did was look at, so it's thin films, platinum gold that have been hit, like peeled off from the substrate, so they're highly deformed, and then heat treated to induce segregation to the dislocations that have been formed. And it's one of the systems that actually has a big miscibility gap. So the plan was to also see how solids would distribute along some of the dislocations and defects and so on and so forth. And what we could actually go down to is look at, so Wright did some pretty TEM and then some atom probe. And so here you can see a low angle boundary, for example, with the segregation that will be on the split dislocation on whatever width. And then we did some comparison with the atomistics. And then you see some stacking faults and some Thomson tetrahedra and all of this. And you can measure locally what is the composition of these different beasts. And they're all a bit different. Some of them will be really like a tiny tube. Some of them will be split with segregation on the faults and on the partials. And you can see here, that's one of these stacking fault tetrahedron with segregation on.
Nice.
Yeah, it's really beautiful work. But it goes to show the strength of the technique when we do things properly.
That's really nice.
So if you want the link, I'll just send it to you afterwards.
Yeah, that will be really nice. Yeah. So we are trying to do some phase field dislocation dynamics to look at segregation and what happens at dislocations and stuff like that.
Yep. Okay. Really yeah, this could be interesting. Yep.
Yeah.
Yes. So they didn't do phase field in that case. They did MCMD and then
MCMD, right? Yeah. So we have also done some MCMD, or doing some MCMD to look at copper aluminum, whether aluminum atoms go to stacking faults and stuff like that.
Okay.
But yeah, so we have both the interests, so it will be really useful.
It's good. Yeah, I'll send it to you right after. I mean, I think the behavior will be very dependent on the thermodynamics and the strain, and so the matrix itself will probably play a role.
Right.
But I think, to me, this is the best work that's been done at pushing these boundaries of trying to compare the experiments and the simulations on a level that is really quite high. Mostly because we could really determine what each object that we are looking at, what is it? And we have the resolution that we need to actually point, this is what we're looking at, this is what we're looking at. And then we can measure the composition and then compare this to I think they did DMD and MCMD and compare the results. So I think all of this, it's quite beautiful work.
Nice.
Probably one last question from my side. If we have pores in the structure.
Yes.
Does it
Yeah, so that's a very tricky question. It will not reconstruct properly for many reasons, but mostly the trajectories of the ions are determined by especially in the early stages, by the shape of the surface, right? So the ions will be projected more or less normally from the surface initially. Now, if you have a pore, something that looks like this, the ions will have trajectories that are crossed. But then as soon as they're out, they will be projected based on the general geometry of the specimen, right? So what is going to happen is that depending on the size of this pore or void with respect to the overall specimen, you might end up with regions that are very dense or regions that are not so dense. And it's really quite tricky to interpret at times. We've done some work over the past couple of years. If you want, I can also send you a paper. It's quite nice, actually, but maybe I should stop saying that we do nice work. But I'm happy to do what I do, right? So
exactly.
I mean, it's one of the good things about our job in principle. So this is a collaboration with friends from Oak Ridge National Lab. So they made these needles, and then you can see, so these are irradiated samples, nickel chrome, cobalt chrome, I think 33%, like it's one of these medium entropy type bullshit. But anyway, so here it's been irradiated and it's full of voids, small voids. So they can see them from the stem. And then in the atom probe, we actually saw this fluctuation of the point density. And there were either, the point density was either doing this or sometimes doing more of a W shape. So sometimes it just drops and then increases and then drops again. And this all depends on two things, the size of the void, but also whether there is a layer of different composition on the rim of the void. And we determine this based on simulations of the ion trajectories when you have a hole inside of the needle. So we could find either this case or that case, but this one didn't happen. And that's because as soon as you had something that was a bit bigger, it had also a different composition on the inside. So yeah, there was quite a lot of head scratching as well. But it was interesting in many ways to look at that, because very often we thought we saw small voids, but we didn't have the correlation with the TEM to really show that, yes, there is a void exactly there. So yeah, I can send you this afterwards as well if you want.
Sure, that would be great. Yeah.
Cool. Okay.
Thank you. If there are no more questions, I don't see any raised hands. So I would like to thank you once again for yes, virtual claps. So I would really sorry. So Raja has.
I want to take away my hand, but it doesn't count.
Oh, I see. Sorry. Okay.
Sorry about it.
Everyone's clapping for the wonderful presentation, for bringing us the state of the art, really cutting edge among the techniques, and then showing us various examples of what can be done. We have several students who are working a little bit on APT. We have the center with IIT Madras that we share. And we would really like some guidance. So I think this was a starting point, and I hope they will be able to reach out to you or to one of the group members whenever you can spend some time. We can do these
that's
focused
really,
discussions on them.
Yeah, that's no problem. And especially on different aspects, if you want to get into halogen now, we have a student who is about to start writing her PhD thesis now, and she's been doing a lot of work on this, and she knows quite a lot about this. And I'm sure she would be delighted to interact with you guys. So
that'd be great.
Depending on which aspect, you just ping me, and we'll find a way.
Sure. Thank you for being so approachable. It was wonderful having you.
Thanks a lot for having me.
Yeah, all of you have a nice evening, and I think we can close the session, Guru.
Yeah, we can close.
Thanks a lot.
Thanks a lot.
Thank you.
You take care. Bye-bye.
Bye.
Take care. Bye.